Hello everyone. Today we'll talk about row operations or elementary row operations. This is material from 1.1 of the text. So let me start out by recalling, kind of our basic question for much of the semester will be, given a system of linear equations. So you could have, 5 equations and 3 unknowns or whatever it is. You always want to ask the same kind of 2 things. Is the system consistent? Does there exist any solution? And if so, how many solutions are there? Okay, and so I should say, so the first question is what we sometimes refer to as the existence question. The second one is the uniqueness. I should say that later in the semester, we're going to talk about maybe a better version of question 2. Actually, what are they? So we're going to be able to describe the solutions in a kind of systematic way. But for now, we just want to know how many solutions are there. Now, as you know, any system has 0, 1, or infinitely many solutions. So once I know that it's a consistent system, it's just a question of is there one or is there infinitely many? And let me do this with an example. So recall from last time that we're going to be dealing with what are called augmented matrices. So these are ways to represent a system. This is a 2 by 3 system. There's 2 rows and 3 variables. Just to remind you, this is actually referring to this is encoding the system 2x1 plus 4x2 plus 8x3 equals minus 2, and 3x1 plus x2 equals 4. And again, we're going to be slowly, I'm never going to write down the system itself. I'll write down the augmented matrix because it's the same information. Okay, and so, again, the strategy here will be give me one of these augmented matrices. I'm going to now transform it into a new system with the same solution set. So I want to manipulate the equations so that I don't change the actual solutions, but I have a new form that's easier to analyze. And the moves, the kind of ways that we change this system will be called elementary row operations. So let me just write these down so you have them in one place. So there's 3 flavors. The first one is maybe the most important, is that you can replace any row with the sum of itself and a multiple of another row. Okay, let me call that the replace. The second one is you can interchange any 2 rows. So you can swap row 1 and row 5 if you had a system that big. 3 is you can scale any row by almost any number. It's any non-zero number. Okay, so you can take every entry in that row and just scale it by 5. Okay, now the important fact for us is that these, as I said before, these row operations, these changes to the system, you end up with a new system. The numbers will be different, but the underlying solution set won't change. So performing any row operation preserves the solution set of the underlying system. So in particular, if you gave me a system that had no solution, the new thing would have no solution. If you gave me a system that had 1, 5, minus 2 as a solution, the new one would also have that solution. And why do these not change the solution set? I don't want to really go through the details here, but hopefully, especially number 2 and 3 should be very clear that if I interchange 2 rows, if I just take this equation, make it the second equation, right? If I swap these 2, that doesn't change the system actually. It just, we're just reordering which one we call the first equation. Number 3, if I scale any row if I scale the first row here by 5, if I scale every entry here, that doesn't change the system, right? Because it doesn't change the solution set because if there's something that works in this equation as it is, it'll still work if I multiply the left-hand side by 5 and the right-hand side by 5. And similarly, number 1, if you think about it, what I'm doing here is I'm taking a row that needs to be satisfied in my system, and I'm adding a multiple of another row to both sides. So if the equality held before with those two equations, then when I take the multiple of the row, add it to the row where it was satisfied, it will still be, right? So if 5 equaled 5, and then I added, 2 to each side, that would still work. And if it didn't work before, it still wouldn't work. So, again, these row operations don't change the underlying solution set. One piece of notation here is that two matrices, we say that they are row equivalent if you can, let's say, obtain one from the other via these row operations, Okay, so let me give you guys an example of what these look like for our matrix here. Let's see, so I want you to be able to see this list here. So let me just go back to the example that we had before. So I should say, again, the row operations are these moves I can make. Of course, we're not going to just make them randomly. We want to, the idea is we want to perform these row operations in a way that gives us a new system, again, with the same solution set, but where we can more easily identify the consistency and the number of solutions. So, so let me just say this, write this down. The strategy will be we want to perform row operations. I'm going to say left to right and top to bottom. And what we're going to be doing is we're going to be clearing variables below what are called the pivots. Okay, so I'll define that precisely later, but just to introduce that notation here. Okay, so again, let's do this via an example. So here's the matrix you gave me, right? This is the system I'm considering. And so I should say now a pivot will be an entry I see in the matrix. As I look at the first row, I want to look for the first non-zero entry coming from the left. So this is a pivot because it's the non-zero entry in the top left. And I want to clear below, okay? Now, I can clear below by taking a fraction of 2 and adding it to 3. So let me just show you that I can actually use my row operation 3 to make my life a little bit easier. I notice that all the entries in row 1 are multiples of 2. So what I want to first do is scale row 1 by 1/2. Okay, so what that gives me is 1, 2, 4, minus 1, 3, 1, 0, 4. Okay, so again, I didn't touch row 2. I just scaled everything in the first row by 1/2. That doesn't change the solution set. Okay, and so now the pivot is 1, has a value of 1, so it's going to be easier now to clear below. What I'm going to next do is I'm going to replace, so I'm going to use one of my row operations of flavor 1, and I want to replace row 2 with minus 3 times row 1 plus row 2. Okay, so minus 3 times row 1 plus row 2. What that gives me is I don't touch the first row. I replace row 2 with minus 3 times row 1 plus row 2. So minus 3 times 1 is minus 3 plus 3 is 0. That's why I chose it. Minus 3 times 2 is minus 6 plus 1 is minus 5. Minus 3 times 4 is minus 12 plus 0. Minus 3 times minus 1 is 3 plus 4. This is 7. Okay. Okay, and so, this is a small example, but what I would do now is go to the next row. So I'm going left to right, top to bottom, as you would read a book. So if I look at this matrix, I go left to right, the next row is here, I go left to right, the first non-zero entry I see is minus 5. So that's going to be my other pivot, so maybe I can just say now that these are going to be what are called the pivots. But there's nothing to do now because there's no entry below it. So I can stop here. The matrix is in what's called echelon form. And I'll define this precisely in the next lecture. But the point here is we can already tell, we can determine if the system is consistent. Okay, so how do I know this? Well, let me just do this again kind of with this example. What I see right now is that row 2 is telling me that minus 5x2 minus 12x3 equals 7, right? And in other words, this should actually be minus, right? Minus 12x3 equals 7. So in other words, this is telling me that minus 5x2 is equal to 7 plus 12x3, right? And so what this is telling me is that, in fact, x3 can be anything. So x3 is what's called the free variable. Let me underline that because that's important. Can be anything. But then it forces x2 to be, we can solve for x2. If I knew that x3 was 1, then I plug it in. It's 7 plus 12 is 19. I can solve for x2. So x2, this determines x2, which is what it's going to be called a pivot variable. And then what happens now is that from row 1, I see that x1 plus 2x2 plus 4x3 equals minus 1, right, just by copying down the new row 1. So what this is telling me now is that x1 is equal to minus 1 minus 2x2 minus 4x3. So if I know what x2 and x3 are, it forces what x1. So this determines x1. And the language that we're going to use is that these are both called pivot variables, x1 and x2. Okay, but the main idea here is that I can already tell, so maybe the punchline is that, can I fit it here? The punchline here is that the system is consistent. It has a solution, but in fact, I had a choice of what x3 could be. So in fact, we have infinitely many solutions. Okay? And let me just kind of wrap up with one observation here that's going to be important as we move forward. So here's another kind of important fact here. So a system is going to be consistent if and only if in its echelon form, which I haven't quite defined precisely yet, but we'll get to that. We do not have any row of the form, so 0, 0, 0, and then in the augmented part we have something where it's non-zero. Okay, so what I'm trying to describe here is that I've got the big matrix. The matrix is, maybe has 5 rows or something. But as long as we never have 0, 0, 0, 0, 0, 6, we're good. I should just notice that if, it should be clear that if you have 0x1 plus 0x2 plus ... plus 0xn equals, say, 17, if you had something like that, that's clearly an inconsistent system because, well, what am I going to do here? I can't, whatever I choose for x1, x2, x3, etc., it's going to get killed on the left-hand side, and I can never have that equal 17. So this is clearly a problem, clearly inconsistent. But the kind of important thing to realize is that if you never have a row like that, the system will be consistent. Okay? And then if consistent, the other thing that we're kind of noticing here is that if consistent, the system has infinitely many solutions, if and only if there exists at least one what's called free variable. Okay, so there's kind of 2 facts here. There's fact 1 and fact 2. Okay, and so this is, again, we're not quite making things precise here, but I want to give you the sort of top-down perspective on this. We'll continue next time with a bit more detail. So we'll see you then.